You remember yesterday, but not tomorrow. You've seen cups shatter into pieces, but never seen pieces spontaneously jump together into a cup. You've watched ice melt, but never seen water suddenly freeze without being cooled. Time seems to move in one direction only from past to future. But here is the strange part. The fundamental laws of physics don't care which direction time flows. Newton's laws, Maxwell's equations, even Einstein's relativity and Schrodinger's equation, they all work perfectly well forwards or backwards in time. If you filmed molecules bouncing around and played it backwards, nothing would look wrong. The laws permit it. So where does the arrow of time come from? Why does nature distinguish past from future when the laws say it shouldn't? The answer isn't in the equations. It's in counting. It's in probability. It's in the simple fact that there are vastly more ways to be disordered than to be ordered. And once you see this, everything broken cups, aging, memory, the evolution of the universe itself falls into place. Let's start with something simple. Imagine a box with a barrier down the middle. On one side, you've got gas molecules, let's say 100 of them bouncing around. On the other side, nothing, vacuum. Now remove the barrier. What happens? The gas spreads out. The molecules diffuse into both sides of the box until they're evenly distributed. This seems obvious. Gas expands to fill available space. But now ask, why doesn't it ever happen in reverse? Why don't all the molecules, purely by chance, end up on one side again, leaving the other side empty? Subscribe and like for more videos that explain what's really happening beneath the surface, because this question leads straight to the deepest mystery about time itself. The answer is, it could happen. The laws of physics don't forbid it. Every collision, every motion is perfectly reversible. If you filmed the molecules spreading out and played it backwards, nothing would violate physics. But even though it's allowed, you never see it. Why? Because of numbers, of statistics. There are vastly more arrangements where molecules are spread evenly across the box than arrangements where they all on one side. Imagine flipping 100 coins. How many ways can you get 50 heads and 50 tails? Lots. How many ways can you get 100 heads? 1. The even split isn't special because of some law. It's special because there are overwhelmingly more ways to achieve it. Same with the gas. There are trillions upon trillions of microscopic arrangements corresponding to spread evenly, and only one corresponding to all on one side. The system isn't trying to spread out. It's just that almost all possible states involve being spread out. This is entropy. Entropy is a measure of how many microscopic arrangements correspond to the macroscopic state you observe. High entropy means many arrangements. Low entropy means few. And here is the key. Systems naturally evolve from low entropy to high entropy, not because of a law forcing them, but because high entropy states are vastly more probable. It's not that molecules prefer to be disordered. It's that disorder is the default, simply because there are more ways to be disordered than ordered. Now let's apply this to something you see every day. You drop a cup. It shatters. Pieces fly everywhere. Why doesn't it ever unshatter? Why don't the pieces leap off the floor, fly together, and reform into a cup? Again, the laws of physics permit it. If you could reverse every molecule's velocity, every single one in the cup, the floor, the air, the cup would reassemble. But the number of arrangements where molecules are moving in just the right way to make that happen is infinitesimally small compared to the number of arrangements where they re-knot. The shattered state has enormously higher entropy than the intact cup. Once the cup breaks, the system is in a high entropy state, and it stays there, not because the laws forbid reassembly, but because the probability of reassembly is effectively zero. This is why we perceive time as flowing forward. We define the future as the direction in which entropy increases. We remember the past because memory is a low entropy configuration of neurons that formed when something happened. That record persists because high-entropy brain states don't spontaneously organize into low-entropy memories pointing backward in time. The arrow of time isn't built into physics. It's built into probability. Here's where it gets deeper. The second law of thermodynamics says entropy always increases in an isolated system. But why? Why should the universe care about increasing disorder? It doesn't. The second law isn't a law like F equals ma. It's a statistical fact. If you start in a low entropy state, you're vastly more likely to end up in a high entropy state simply because there are more of them. The universe doesn't prefer disorder. It's just that disorder is overwhelmingly probable. But here's the paradox. If entropy always increases, why was entropy low in the past? If the universe is evolving toward maximum disorder, how did it start in a low disorder state? This is the real mystery. The Big Bang began with incredibly low entropy matter and energy concentrated, uniform, highly ordered. Since then, entropy has been increasing. Stars form and burn out. Galaxies spread apart. Heat disperses. The universe is winding down toward a state of maximum entropy where nothing interesting can happen anymore, what physicists call heat death. But why did it start low? We don't have a complete answer. The initial low entropy of the universe is one of the deepest unsolved problems in physics. Maybe it's a consequence of the laws governing the very beginning quantum gravity, inflation, something we don't yet understand. But whatever the reason, that initial low entropy state is why time has an arrow. It's why you age. It's why the universe has a history. It's why cause precedes effect. And here's the philosophical kicker. You exist because of entropy. Life is a process that locally decreases entropy. You take disordered nutrients and organize them into structure, into cells, into thought. But you can only do that by increasing entropy elsewhere. You breathe, you metabolize, you radiate heat. The total entropy of you plus your environment always increases. Life doesn't violate the second law. It exploits the gradient between low and high entropy states. Without that gradient, without the universe starting in a low entropy Big Bang and evolving toward disorder, there would be no energy flows, no complexity, no structure. No stars, no planets, no chemistry, no you. Feynman understood this beautifully. He explained that the distinction between past and future isn't fundamental, it's statistical. The laws of physics are time-symmetric, but the universe isn't. We happen to live in a universe that started with low entropy, and that single fact explains why eggs break, why we remember yesterday, why we age, why the cosmos evolves. Time's arrow is real, but it's not written into the equations. It's written into the initial conditions. So when you drop a cup and it shatters, you're not witnessing a law of nature. You're witnessing probability doing its job. The cup doesn't reassemble not because it's forbidden, but because the odds are so astronomically against it that you could wait longer than the age of the universe and never see it happen. Time flows forward because almost all roads lead to disorder, and we started on a rare, improbable road of order. That's the truth about past and future. Time isn't a thing that flows. It's a direction defined by the increase of entropy. And that direction exists only because the universe began in an extraordinarily unlikely state. We don't know why, but we know that without it, there would be no past to remember, no future to anticipate, and no one around to wonder why.